You know that box on your desk, or maybe the laptop you're watching this on? We use these things every single day. But for a lot of us, they're still kind of like a magic box, right? We type, stuff happens. We click, things just appear. Well, in this explainer, we're going to unbox that magic and actually see how it all works. I mean, seriously, have you ever stopped to think about what's actually going on inside? How does a simple click on a mouse turn into a video streaming from halfway across the world? Or how do your keyboard taps become an email that gets there in seconds? Well, let's find out. Okay, so let's get right down to it. At its very heart, a computer really only does three things. It takes input, that's you telling it what to do. Then it processes that information, that's the computer doing its thinking. And finally, it gives you an output, the result of all that work. Input, process, output. Believe it or not, that simple little loop is the secret to everything a computer can do. Now, to really understand that loop, we've got to look at the two fundamental parts of any computer. The absolute easiest way to think about it is, well, the difference between a body and a brain. This is the core idea behind hardware versus software. It's a really simple distinction, but it's absolutely crucial. Hardware is all the physical stuff, the things you can actually touch and see. The screen, the keyboard, the little circuits inside. But the software, that's the invisible set of instructions that tells all that physical hardware what to do. So the hardware is the body, but the software is the mind that tells that body how to move. So your hardware includes all the obvious stuff, right? Your monitor, your keyboard, your mouse, but it also includes the most important part, the central processing unit, or CPU. You can think of the CPU as the main chip that does all the heavy lifting, all the thinking. These are the real, tangible pieces of the puzzle. And the software? Well, that's everything else. It's your operating system, like Windows, which is kind of like the manager for all the hardware. And it's all the programs you actually use, like a word processor or your web browser. Software is what breathes life into the hardware and makes it do useful things for us. All right, so we have the body, the hardware, and we have the brain, the software. Now let's look at how they have a conversation. And this brings us right back to that core loop we talked about, input and output. This is literally how we talk to the computer and how it talks back to us. Remember that three-step dance? Here it is in action. It all kicks off with you giving some kind of instruction, an input. Then the computer's hardware and software team up to process it. And finally, it shows you the result as an output. This isn't just a one-time thing. It's a constant, incredibly fast cycle that's happening thousands of times a second whenever you use your machine. So how exactly are we giving those inputs? With input devices. Every single time you type something, click your mouse, scan a picture, or even talk into a microphone, you are sending brand new information into the computer. You're starting the conversation. And how does the computer answer back? With output devices. When you see words appear on your monitor, or a page slides out of your printer, or you hear music from your speakers, that's the computer giving you the results. That's the output. That's its side of the conversation. Okay, so while the computer is busy processing all this information, where does it keep everything? I mean, it needs a spot to hold data while it's working, and another place to store things for later. This brings us to what I like to call a tale of two memories. The best analogy for this is to think of your workspace. Primary memory is like your actual desk. It's where you keep everything you're actively working on right now. A big part of this is RAM, which is your open workspace. It's super, super fast. But when you turn the computer off, the desk gets cleared. Then you've got ROM, or read-only memory. Think of that as the instruction manual that's bolted to the desk. It has the permanent startup instructions that can't be changed. But what about the filing cabinet in the corner? Well, that's your secondary memory, like your hard disk. It's where you store everything for the long haul. It's a bit slower to get stuff out of, but it keeps your files safe and sound even when the power is off. So we've got hardware, we've got software, we have a way to talk to it, and a memory to store things. When you put all of that together, what you get is an unbelievably powerful tool. But what exactly is it that makes it so powerful? I mean, just think about it. We use them for absolutely everything, don't we? School, banking, work, surfing the web, just plain old entertainment. They've become part of our lives because they have a few unique advantages. Some actual superpowers, you could say. First up, it's incredible speed. A computer can whip through billions of calculations in a single second. It's a speed of thinking that is just, well, it's way beyond what any human can do. Next, there's accuracy. As long as you give it the right instructions, a computer doesn't make typos. It doesn't get tired or distracted. It will perform a task with perfect precision every single time. Then you've got storage. This goes right back to that filing cabinet we talked about, the secondary memory. A computer can store an absolutely gigantic amount of data in a tiny, tiny space. We're talking entire libraries that can now fit right in your pocket. And finally, multitasking. You know how it seems like a computer is doing a million things at once? Well, the crazy thing is, it's not. Its processor is just switching between all those tasks so incredibly fast, millions of times per second, that it creates the perfect illusion of doing everything at the same time. It just handles it all without breaking a sweat. So there you have it. We've unboxed the machine, we've seen the hardware body, the software brain, and that simple loop of input and output that makes the whole thing tick. But that leaves us with one last big thought. We've just looked at the basics here. So what happens when all of this gets a billion times faster and a billion times smaller? Thanks for joining this explainer.